Hello, this is Jack Jackson. We're going to continue our look at power series and intervals of convergence. So in the last video, we talked about trying to find the domain of a power series. A little bit, we introduced the idea of power series. And we got to this point where we were wanting to find the ratio test or use the ratio test to find a interval of convergence. And of course, when you do the ratio test, you take a term here, c sub k, x minus a to the k there. Take that and put that in the denominator. Put in the next term, c sub k plus 1 times x minus a to the k plus 1 in the numerator. Do the absolute value, take the limit. Look at what always happens. The x minus a to the k's always cancel, leaving an x minus a. The absolute value of that can be split off as a factor and then brought out in front of the limit sign, so you always have this. So you're always going to have this x minus a absolute value out front, and you just have to do the limit of the ratio of the coefficients. So rather than going through this every single time, we're going to start with that. So the question is, what happens on this limit? Either the limit doesn't exist, for example, it approaches infinity. In this case, the radius of convergence is 0, and the only thing that's going to work is x equals a, which always works. If you have that limit is some limit L for this limit of the ratio of the successive coefficients. Then that turns out that that 1 over L turns out to be the radius of convergence, and you get the interval going from a minus 1 over L to a plus 1 over L. It converges absolutely on that interval, and it diverges to the right of a plus 1 over L and to the left of a minus 1 over L. What we don't know for the ratio test is what happens when x equals a minus 1 over L or x equals a plus 1 over L. So you have to then check those endpoints separately. Take whatever number you have here, plug it in for x. That gives you a sequence of constants, a series of constants, and work out what that limit, work out if that has a limit or not, if it converges. Okay, and same way for the other end. So we're using all of our different convergence tests from before, like, comparison test, limit comparison test, integral test, not the ratio test because we used it here, but maybe the alternating series test and so forth. Okay, so the other option is that this limit might turn out to be 0, and that's sort of the best case option. For number 1, you don't have to check the endpoints, and number 2, it converges for all real numbers. So let's look at some examples. Before we get into one where we actually use the ratio test to work out, let me just remind you one that we already know. We want to find the interval of convergence of the following power series, the sum from k equals 1 to infinity of just x to the k. Well, that's 1 plus x squared plus x cubed plus x to the fourth, etc. That one is actually just a geometric series where the base is x. And we've already shown that a geometric series is going to converge when that base x is between -1 and 1 exclusive. So it diverges when x equals -1 and it diverges when x equals 1. Diverges for bigger than 1, less than -1, but it converges in between there. Okay, and it actually converges absolutely there. So we know that the sum from k equals 1 to infinity of x sub k, not only do we know it converges, we know what it converges to. It converges to 1 over 1 minus x. The first term, of course, is 1. Right here, if we start at 1. And that is, that's what we get here. Actually, I take that back. We want this to start at 0. So it starts at 1 plus x squared and so forth. Okay, there we go. So now we started at 0. The first term is 1, and then so that's 1 times 1 over 1 minus the base. And so that's the geometric series, and it, oops, got to fix it here as well. Start at 0. And that one is convergent there. Okay, we already did that earlier. So now let's look at another one here. Find the interval of convergence of the following power series, k factorial times x minus 3 to the k from k equals 1 to infinity. And we start by applying the ratio test. If x is not 3, then we have the absolute value of x minus 3 times the limit as k goes to infinity of k plus 1 factorial over k factorial. Well, that cancels down to just k. Of course, k plus 1 factorial is k plus 1 times k factorial. The k factorials cancel. So this is the limit of, I should say k plus 1. Same thing anyway, though. It's still infinitely big, right? And so that goes to infinity. And so this is infinity. So it diverges all the time except when when x equals 3, the place where it's centered. And so the domain is just that set containing 3. When x is 3, all of these are 0. All the terms are 0, and it does converge. Okay. Find the interval of convergence for the following power series. -5 to the negative k, x minus 4 to the k. Okay, so let's work that out. Again, you always have the absolute value of the x minus a, the x minus 4 in this case, and then the limit of the ratio of the coefficients. So you have the original coefficient in the denominator, you put k plus 1 in place of k there. So this becomes negative k minus 1 there. And you can divide this out by subtracting exponents, and you're left with 5 to the negative 1, or 1 over 5. Well, that's a constant. That limit is 1 over 5. So the radius is going to be the reciprocal of that, which is 5, which you'll see here in just a second as we multiply both sides of this by 5. Well, first of all, this is going, by the ratio test, this is going to converge absolutely when that limit, the overall limit, including the x minus 4 in absolute value, is less than 1. And so you multiply both sides of this by 5, and we see that we have this is an interval centered at 4 with radius 5. It goes from 4 minus 5 to 4 plus 5, or in other words, from -1 to 9. So we would say the radius of convergence is 5, and the center is 4, and the interval is -1 to 9. Now what we don't know is what happens at x equals -1 and at x equals 9. We know for bigger than 9, x is greater than 9, or for x is less than -1, it diverges. And we know that it converges absolutely for the stuff between -1 and 9. But what happens right at -1 and right at 9? Well, we have to check those, and we have to check those separately. First, let x equals -1 and just see what happens. So here's our series, and if you plug in x equals -1, we're to here, right? So -1 minus 4 is -5. Okay, wait, if you multiply these together, you always get 1, and we're adding up 1. 1 plus 1 plus 1 plus 1 plus 1, which clearly diverges to infinity. So -1 is not included, so we have an open open parentheses on the left side here. Well, what about 9? Okay, let's try that. Put in 9 here for x. There we go. So we're letting x equals 9. 9 minus 4 is 5. Multiply these together, you get 1. So you get -1 to the negative k. So the underlying sequence is, so you start at 1. So that's negative. So it starts at -1. -1, and then 1, -1, 1, -1, 1. But we're going to add those up. So the sequence of partial sums is -1, 0, -1, 0, -1, 0. Well, that doesn't have a limit. So, well, that means we can't put in x equals 9 and get a reasonable answer out of this either. So the domain is just an open interval from -1 to 9. And of course, the power series converges absolutely on that. Okay, here's another example. Find the interval of convergence for this one here. Really, hey, you should probably try one of these yourselves. Why don't you try this one before we go on? Press pause. Come back when you got it worked out. Well, how do we start? We always start with the ratio test, right? And we always have this. This is x plus 2, so we have the x plus 2 in parentheses out here. That's x plus 2, of course, is x minus a negative 2. So this one is going to be centered at negative 2. Then you do your ratio of the coefficients at successive k values. So you put 1 over k in the denominator, put in k plus 1 and place the k there, which is 1 over k plus 1. So this, we do the invert and multiply stuff here. This becomes k over k plus 1. That limit is 1. We've done that kind of limit many times. And so we get our radius of convergence is 1 over 1, which is 1. And so this goes between negative 1 less than x plus 2 less than 1, which add negative 2 to every negative 2 to all three sides. You get negative 2 minus 1 to negative 2 plus 1. So it's centered at negative 2 right in the middle of this interval, and it goes 1 to the left and the right. So the radius is 1, and the center is negative 2. And that gives us, of course, negative 3 and negative 1. And so we know for x is strictly between negative 3 and negative 1, this series is going to converge absolutely. We know for x is greater than negative 1, it diverges. For x is less than negative 3, it diverges. What we don't know about is what happens when x equals negative 3 or x equals negative 1. We have to check for those two things separately because the ratio test is inconclusive when this limit equals 1. So here we go. We try them one at a time. We just let x be negative 1, for example, and then we plug in here. We plug in the x right there is negative 1. 2 plus negative 1 is 1. 1 to any power is 1. So we just have the sum of 1 over k, where we're familiar with that one by now. That's the harmonic series, a p series with I would call it p is negative 1. That diverges to infinity. So x cannot be negative 1. Negative 1 is not in the domain. We leave that one a brown parentheses on the right. What happens when x is negative 3? That's the other one we have to check, right? So plug in negative 3 here. Negative 3 plus 2 is negative 1. So this is negative 1 to the k times 1 over k. That is the alternating harmonic series. We've done that one several times as well. That one we know converges by the alternating series test. If we had to work out the test, we would show that the absolute value of this is decreasing. 1 over k is always, 1 over k plus 1 is always less than 1 over k. So this is decreasing in absolute value. And it is, let's see, what else do we need? We need the limit of this is 0, which was true. And it's alternating in sign, which we can see from this right here. So that's enough to say this is going to converge by the alternating series test. So that means x equals negative 3 is part of the domain. So it converges absolutely for x's strictly between there. It converges conditionally for x equals negative 3 and diverges otherwise. The domain or the interval of convergence is x is in this interval, closed interval from negative 3, closed on the left, negative 3 comma negative 1, open on the right. In other words, negative 3 is less than or equal to x, which is less than negative 1. All right, here's another one. Why don't you try this one? Press pause now. All right, we have the sum from k equals 1 to infinity of 1 over k cubed plus 1 times x minus 7 to the k. So there's our x minus 7 absolute value up front. And then we do the ratio of the coefficients here, where we put the original coefficient on the denominator. And we put the numerator the same thing with a k replaced by k plus 1. Okay, so this is k cubed plus 1 over k plus 1 cubed plus 1. So I'm going to multiply by 1 over k cubed in the top and bottom, and then distribute. So 1 over k cubed times k cubed is 1. 1 times 1 over k cubed is 1 over k cubed. 1 over k cubed distributed in the bottom times the 1 here is 1 over k cubed. Now when I distribute the 1 over k cubed here, I can bring it inside, and it's k plus 1 over k whole thing cubed, which is 1 plus 1 over k, and then cubed. So hopefully you followed that algebra there. And now if we take the limit as k goes to infinity, all these little fractions here and here and here with k in the denominator, they go to 0. That one, that one, that one, that one. Then the top is 1. The bottom is, well, it's also 1. So this whole thing is just 1. So our radius of convergence is 1, centered at 7. So it goes from 7 minus 1 to 7 plus 1, which is 6 to 8. Remember, this converges when this limit, which is now just the absolute value of x minus 7, is less than 1. That's the way the ratio test works. Converges absolutely. Again, we don't know what happens at 6 or 8 yet. And I don't know why that says 14. It should say 8. So for x is less than 6 or greater than 8, we know it diverges. Between 6 and 8, it converges absolutely. We have to check the endpoints. This time, I can actually check them at the same time. Whether I put in 6 or 7, no, 6, not 6 or 7, 6 or 8, then x minus 7 absolute value is 1. And if I look at the absolute value of that, we get 1 over k cubed plus 1. So we're going to see that this converges absolutely. And so I can kind of check them together here. This is less than 1 over k cubed, which is a convergent p series. P is -3, the way I write it. And so the series of absolute value of terms is term for term less than the convergent series with p equals -3. And so the series converges absolutely by the direct comparison test. And I checked it really both for 6 and for 8. Therefore, the series converges on both of those values. So that is, I don't know where that 14 came from, 6 to 8, including the 6 and the 8. So the series converges absolutely on that entire interval, including the endpoints. All right, here's another one for you to try. Work this one out yourself. Press pause now. Okay, let's try this out. Hopefully you've worked this yourself. All right. So this time I'm going to, because the power is not just a x power, k power here, I'm going to go ahead and work it out to see what happens with that in there, rather than just to pull out an x, absolute value of x out front. Okay, so we take this thing to the, just like it is in the denominator. Hopefully I copied that over correctly. Yeah. Now we have to take this same thing and put in the top, but replace the k's by k plus 1. There's a lot here, so let's be careful. That k factorial becomes k plus 1 factorial. That k is k plus 1, so we got k plus 1 factorial there. This is 2 parentheses k plus 1 for the power there, base of 2. Here's the base of x. This is 2 times parentheses k plus 1, and that power is k plus 1. Now, actually, these, okay, so I'm going to just do the invert and multiply stuff. So the stuff in the bottom here goes to the top. Stuff in the top here goes to the bottom. This one stays where it is. And I think that's what I have here. So this here, let's just check. Make sure I didn't make any mistakes. This part here, these two terms, these two factors are right here. This factor here should have gone, these factors here in the bottom should have gone to the top. These are down in the bottom here, and these are staying in the bottom here. Okay, so I think everything's where it needs to be. Now let's see if we can clean up just a little bit. First of all, I can do this distributing here. 2 times k plus 1 is 2k plus 2 plus 1 more is 2k plus 3. And same thing here. And k plus 1 is k plus 2. Okay. These actually cancel down to just -1. Although really, honestly, I didn't have to worry about that because it's inside the absolute value. That's just going to be 1 anyway. Could have just discarded that earlier. All right, let's see what we can do as far as canceling. Okay, here's a k plus 1 factorial, and here is 2. So those cancel completely. K plus 2 factorial is k plus 2 times k plus 1 times k factorial, which cancels with that factorial. So now that guy's gone, that guy's gone, that one's gone, replaced by this. The negative ones are taken care of. All right, let's look at the 2's. There's 2 more 2's in the bottom than the top, so we get a 2 square, or 4, in the bottom. And the only thing left are the x's. There's 2 more x's in the top than the bottom, so we get an x squared in the top. Now, the absolute value of x squared is x squared, and I can bring that out front. Absolute value of 4 is 4, so I can bring that out front. Of course, it's in the denominator. So we have x squared plus x squared over 4 in the out in front. And then I'm left with 1 over k plus 2 times k plus 1. Oh, that limit goes to 0 regardless of what's out front. And so we get this is less than 0. I mean, this is 0 all the time for this limit, and that's less than 1 no matter what the x is. And so this one converges for all the real numbers. This one's the nicest one because, number one, it works for no matter what you, and most importantly, it works for no matter what you put in for x, but also you don't have to check the endpoints, so it's a little bit less work. And so it converges absolutely for any real number for x. And we, of course, we would say this, this is radius is infinity on this one. This particular one has a name. This is a power series is called a Bessel function of order 1, J1 of x. And Bessel functions of various orders are used to approximate many important physical phenomena from physics and chemistry, like, for example, the vibration of a drum head, for example, is one example of this. So, you may look at that and say, well, boy, that's kind of a mess. Who would ever need that? Well, yeah, it's actually used in the real world. Okay, so that brings us to the end of this little video. And now I think you've got enough examples there to help you work out several problems of this type. So time to go dive into some homework problems.